Assalamualaikum everyone and welcome to our video visitation. We are group KKC9. Today, we are going to present the finding obtained from the task 1, 2 and 3. The main objective of the assignment is to identify every detail in every task. Over the next few minutes, we will walk you through our finding from task 1, 2 and 3. We'll break down our mathematical formulation, explain our solution procedures and discuss our results before sharing our final conclusion. So, let's dive into task 1. For task 1, we analyze monitoring data from a water treatment process. Our goal was to develop a mathematical model of pollutants concentration over time, estimate when it reached a safe target, and analyze its behavioral trend. Looking at our solution procedure, group 19 square meter gave us an initial concentration of 210, a reading of 126 at hour 4, and a target of 50. We started with the differential equation, which is dc over dt equal to negative kc. Integrating this gives our general formula, which is c equal to a exponent power of negative kt. By substituting our initial condition at time 0, we found A is 210, and next by plugging in our data for our 4, we calculate the decay constant, which is K, to be 0.1277, completing our concentration function. Step 2, we estimate the time to reach our target concentration of 50 by setting our function to 50 equal to 210 exponent by power of negative 0.1277t, and solving using natural logarithm, we calculate t to be exactly 11.2 hours. In step 3, we sketch this concentration profile, plotting concentration on the y-axis against time on the x-axis. As you can see, the exponential decay curve passing through our initial point of 210 for our mark at 126 and reaching our target at 11.2 hours. Finally, in step 4, we analyze this behavior as the graph shows the concentration dropping rapidly at the start of the treatment and then slowing down as the time progresses. This flattening curve occurs because the rate of removal is directly proportional to the amount of the pollutant remaining in the water.
For part A, we substitute our given values for group 19 parameters, which is inductance equal to 0.33 Henry, resistance equal to 660 ohm, and the capacitance equal to 20 microfarad. This transforms our differential equation into second order homogeneous equation with constant coefficients. By completing the characteristic product equation, we complete the discriminant and then to obtain the variables, which is m1 equals to negative 78.87 and m2 equals to negative 1921.13. This mathematically defines the system as an overdamped circuit. Okay, since there is a distinct area, we will set up the general solution form. Next, we apply our boundary initial conditions, which is initial charge Q naught equals to the power of negative 6 coulomb and initial current prime naught equals to 0. By solving these simultaneous algebraic linear equations, we find the constant A and B, which are approximately 2.0856 microcoulomb per A, and B is equal to negative 8.5623 microcoulomb. Thus, our complete particular solution for the charge response is fully determined. For part B, we evaluate the system response at time t equals to 0.01 seconds. Substituting this value into our analytical model yields a remaining charge of 0.948 microcoulomb. In part C, we graph the response profile using proper axis technique. This resulting plot shows a smooth, non-oscillatory exponential decay that originates exactly at our initial value of 2 microcoulomb and quickly subsides towards 0. Finally, for part D, we discuss the core characteristics of the DAQ model. The system exhibits a highly overdamped response because of its internal electrical resistance is remarkably high. This excessive dissipation of energy prevents the signal from experiencing an unwanted oscillations or overshoot. In water monitoring applications, this rapid stabilization is critical to prevent signal distortion and guarantee stable data capture.
I am Ashkar Zuri bin Muhammad Shukri, matrix number 1250121, and I will present for task 3, periodic sampling signal analysis. So, for the first question is determine the series representation of the signal. Our given signal function is ft equal to 22 minus 1.5t over the interval 0 to 22. From this, we know that total period T is 22, which means our parameter L, defined as half of the period, is equal to 11. To find the Fourier series representation, we calculate three coefficients based on our lecture formula, which is AO, AN, and BN. First, for the average value AO, we integrate the function and obtain 5.5. Next, we calculate AN using the cosine integration rule. Substitute into the formula and we need to use the tabular method to integrate the function. As shown in my calculation, we need to know that sin 2 pi is equal to 0 and cos 2 pi equal to 1. It was a basic trigo rules. After the calculation, we got the result is 0. This tells us the signal has no cosine component. Lastly, we need to find the last term, which is Bn, using integration by parts. Substitute into the formula and we get the Bn is equal to 33 over n pi. So, the sine component is exists. Combining this, our final Fourier series representation is 5.5 plus the summation of sine terms, which is 33 over n pi sine n pi t over 11. Moving on to part B, we are required to approximate the signal using the first three non-zero terms. Since an is equal to 0, our three terms come from the constant term, where n equal to 0, followed by the first two harmonic terms, where n equal to 1 and n equal to 2. This gives us our approximation equation, which is 5.5 plus 33 over pi sine pi t over 11 plus 33 over 2 pi sine 2 pi t plus over 11. For part C, we estimate the signal value at the midpoint, where t equal to L over 2, which is 11. When we plug t equal to 11 into our approximation formula, both sine term become sine pi and sine 2 pi, which mathematically equal to 0. Therefore, our estimated value is exactly 5.5. Finally, in part D, we compare this estimate with the exact value by substituting t equal to 11 directly into our original function, which also yields 5.5, and as we can see, the approximation is 100% accurate with 0% error at this specific midpoint. This happened because all the sine wave harmonics naturally cross 0 at the center of the interval, leaving only the average DC value of 5.5. However, to get an accurate shape for the rest of the signal, we would still need to add more higher order terms to minimize the Gibbs phenomenon. In conclusion, the periodic signal for group 19 was successfully represented using the Fourier series, which uniquely consists of only the average DC value AO over 2 equal to 5.5 and sine component Bn equal to 33 over n pi. The three-term approximation yield a perfect 100% accuracy at the midpoint t equal to L over 2. Because all sine harmonics naturally cross 0 at this point. Overall, the Fourier series has proven to be a highly effective mathematical tool for analyzing and estimating for the behavior of this periodic sampling signal.
To conclude, our mathematical formation successfully reached the entire ion monitoring level. The polyethylene decay model from task 1 predicts field treatment timelines. The overtime response from task 2 stabilized our hardware measurements against data noise, and the Fourier series approximation from task 3 accurately converts continuous signal states into digital parts. Together, engineering mathematics provides the required predictive precision and stability for modern water quality